Good morning, people. So this is Saksham Mahajan, fourth year physics majors from ICER Mohali. So I'm going to be talking about this famous phenomenon of Anderson localization, which was also the topic for my term paper for this advanced condensed matter course, which is being taken by Dr. Gautam Sheet. Dr. Philip Anderson stated in his 1958 paper the phenomena of localization in random potential. So this states that basically in the presence of some disorder in the system, so disorder provides you some random potentials. So the eigenstates, they actually tend to localize themselves to some particular lattice sites. So due to this localization, the electrons are not able to hop from different lattice sites, from one lattice site to the other. So they won't be able to carry currents and all. This is obviously marked by then a huge reduction in the conductance. Nowadays, we kind of study this concept more in the form of quantum reflections from different lattice sites. Hopefully, as we move on, you will be able to get what I meant. So we can study this phenomenon of localization by broadly three different methods. So first is by dynamical study. So in this, what we do is we like kind of place an electron at a random lattice site and then study its return probability. So basically, if that electron is able to hop from one lattice site to the other freely, so its return probability should eventually decay. So if it's showing this free particle behavior, it should be able to localize itself over a large number of lattice sites. So its return probability for the initial lattice site should decay exponentially. Whereas this won't be the case in case of localization behavior. So one method to study localization is this dynamical study. Other is we can calculate the localization length and the inverse participation ratio. I'll tell you later on what localization length and inverse participation ratio is and how to calculate them. And the third is the energy spectrum analysis. Again, it states the same thing. If we have a pure point energy spectrum, it indicates that there's localization in the system because electron is distributed over those particular 2-3 lattice sites with very close energy, so we can consider it to be a pure point spectrum. Whereas if we have a continuous energy spectrum, it indicates that electron is delocalized over a large number of lattice sites. Let me first start with the analogy of classical random walk. So I'll first provide you the statement of Anderson localization. It states that metal to insulator transition would exist only in the 3D situations. In case of 1D and 2D systems, no matter how small the distortion or the disorder in the system is, it will always lead to localization in the system. So this theory of classical random walk also gives us kind of same results. Let me explain you how. So we start by considering a one-dimensional symmetric lattice. So an electron is now able to hop either to the lattice site on its left or towards its right with equal probability. So this is the case of a Bernoulli trial, and hence n such trials are bound to follow the binomial distribution. So this is given by the probability of r steps in either direction over the total number of n steps is given by NCR 1 upon 2 raised to power n, which is clearly simple. The formula for the binomial distribution is NCR p raised to power r q raised to power n minus r. So we start that we kind of suppose that the particle starts from origin now and it moves 2n steps in total. And what is the probability that it ends up being at origin again? So it's like it took exactly n steps towards it right and exactly n steps towards left. So the probability for the same will be given by 2ncn 1 upon 2 raised to power 2n, which is approximately equal to 1 upon square root pi n. So the interest lies in calculating the return probability of the particle. If we start the particle from origin and let's say it took n steps, so I'll define this capital random variable capital X. It counts, does the particle return to origin or not? So if the particle is at origin after n steps, its value is taken to be 1 and its value is taken to be 0 otherwise. So the total number of returns in different number of steps will obviously be given by summation over all these different x's at like 1 step, 2 step, 3 step, and so on. So what I'll do now is we'll focus on calculating the return probability. So let's say that rho is the probability that particle returns to origin, and rho r, which is here, denotes the probability of particle returning to origin exactly r times. So it is given. So it will be given by this relation: the probability of returning to origin r times minus probability of returning to origin r plus 1 number of times. So the expected number of returns is given by expectation of x, which is equal to the value of the random variable into the probability. This is how exactly we calculate the expectation value. So expanding this, we get this, and this is a geometric progression if we see carefully, and its result is finally expectation value of x is equal to rho upon 1 minus rho. So here we can clearly see if the value of rho is equal to 1, then the expectation value of x turns out to be infinity, which means that if the particle is left freely, it will return infinitely many times to origin. Whereas if the rho is less than 1, basically the return probability is less than 1, it will correspond to a situation where particle will not return infinitely many times to origin. So now what we will do is we'll perform these calculations over 1D, 2D, and 3D systems. So in case of 1D, as I stated earlier, this is equal to this into the probability of returning into a number of steps by taking exactly n steps towards its right and n steps towards its left. So this is nothing but the sum over this 1 upon square root pi n thing that I showed earlier here. So it turns out to be that this is diverging in nature, which means this is equal to infinity. Similarly, for the 2D systems, this is like 2ncn, 1 upon 2 raised to power 2n, and then which will be equivalent to 1 upon square root pi n, and doing the same calculations for the 2D system, we find that this is again diverging in nature. Whereas in case of 3D systems, if we perform the same calculations, it turns out to be 1 upon square root pi n raised to power 3 by 2. Sorry, I misprinted it to be 2D, it's 3D here. We perform the calculation and we find out that it is less than infinity. So in conclusion, and then as I stated earlier, the return probability in case of 1D and 2D systems, since the expectation value of x turns out to be infinity, means that it will return infinitely many times to the origin, it comes out to be 1. So the probability of return is 1. It means it will surely return to origin once it starts. But in case of 3D systems, this probability is less than 1. It means there's something additional going on in case of 3D systems, which is not there in 1D and 2D, which is actually consistent with the statement that I provided in the beginning of Anderson localization, that the metal to insulator transition exists only in case of 3D systems and not in 1D and 2D. No matter how small the disorder is, in case of 1D and 2D systems, there will always be localization. Means that the return probability will always be 1. Now comes the topic of scaling theory of localization. So what we do is we start from the microscopic scales, like slightly larger than the mean free length of the system, which is obviously necessary to get an insight towards the behavior of the system. And then what we'll do is we'll gradually extend it to the larger length scales. So let's assume that the conductivity inverse of resistivity is a function of length of the system only. So length scale is what we use for scaling. So what I define is, I'll define that this function beta, which depends upon length only through the conductance, which is called the one parameter scaling, and I define beta to be a derivative of ln g with respect to logarithm of length. So I'll talk about now the limiting nature of this function beta. So when we say that conductance is very, very high, the conductivity is very, very high, it's greater than 1. So the classical theory of conduction should work. It's like showing the ohmic behavior. So we have this relation R is equal to rho into L by A. So talking in terms of dimensions, it will be rho into L raised to power 2 minus D, where D is the number of dimensions we have. And performing this calculation, we find that beta in this case turns out to be D minus 2. So in the case when the conductance is very, very high, our beta function just reduces to this value D minus 2. And in the case where the conductance is like very, very less, that is G is very, very less than 1. So this Anderson strong perturbation theory should work, and we expect the localization behavior. So localization behavior is marked by exponential drop in the conductance with the length scale, as I showed earlier. So this will be given by L upon zeta, and this zeta will be the localization length. I'll talk about this later. So this G, so this beta function in this case turns out to be logarithmic function of G, ln(g). So plotting this graph within the same limit, ln(g) limit here and D minus 2 limit here, we see that in case of 1D and 2D systems like dimension 1 and 2, this is always less than 0. So I plotted this beta G here and G here. So in case of 1D and 2D systems, it's always less than 0. Whereas in case of 3D, we see there's a point here. Below this, it's always less than 0, and above this, it's greater than 0. So what this graph shows us for the case of 1D and 2D systems, since the plot of beta G is always negative, this means that the conductance will always decrease with the extension of the length L. So even if we extend the system very small, by a very small change in length, its conductance is going to decrease further, because the plot of beta is always negative. And for this situation in 3D systems, we have this beta greater than 0 and less than 0. We have this critical value of G here. So this shows kind of a transition from metal to insulator behavior. So below this, it shows this insulation behavior, and above this, it's the metallic behavior. So if we increase this length, and if we have G above this critical value, so it will always be marked by increase in conductance, and then it will be other way in the case when I'm in this limit. So this G critical marks the metal to insulator behavior. So this clearly states that localization exists with large disorder, and for the small disorder, there may not be any localization in 3D systems. So talking about the Hamiltonian and its extreme cases, the Hamiltonian that is mentioned here for this tight binding model has been written in the second quantization notation. So this term here with epsilon n, nn, this denotes the on-site probability, on-site energy, which is given by this disorder in the system. And that term here, it mentions the hopping between the nearest neighbor sites from n to n plus 1 and from n plus 1 to n, both bidirectional hopping probability, which is given by G, the hopping parameter here. So talking about the extreme cases for this, let's talk about first the zero disorder case. Zero disorder case means no random potentials here. So Hamiltonian will be marked only by this term. And if we solve this, this is nothing but this free electron gas Hamiltonian. So what we get is this wave function for this plane waves only, where k denotes this wave vector, and J is this lattice height, and D is the number of dimensions that we have in the system. So clearly in the case of zero disorder, this is just nothing but just free electron waves, and the system and the electron is able to hop freely from any lattice height, from one lattice height to the other, to the other, to the other. In case of infinite disorder, we can just neglect this hopping term in front of this potential here we have. So infinite disorder means this is very, very large, and this term can be totally neglected. So what we have is once the electron is there on a particular lattice site, it will stay there forever. So this wave function turns out to be delta function, and so is the epsilon I, the energy of that particular configuration. So the return probability here turns out to be 1 for sure. It's the delta function only, and it indicates a pure point spectrum and hence a purely localized state. Whereas in this case, as we saw, that the return probability is like exponentially decreasing because of this free particle behavior, and the energy spectrum also turns out to be continuous in this case, which indicates a purely delocalized state. So briefly, in case of zero disorder, we have a delocalized state, whereas in case of the infinite disorder, we have a purely localized state. So now I'm going to show you some of the numerical simulations that I have performed regarding 1D, 2D, and 3D lattice systems, assuming a square lattice, cubic lattice, and a one-dimensional symmetric lattice. But before that, I'll provide you a brief of what exactly I did behind. So an insight into the script that I wrote for performing these simulations. So I told you about this epsilon n, which is this random potential due to disorder. So I took it to be uniformly distributed over the interval minus epsilon by 2 to epsilon by 2. So epsilon here kind of marks the amount of disorder that we'll be having in our systems. So it's randomly distributed over minus epsilon by 2 and epsilon by 2. Randomly distributed following this uniform distribution. And now if we write this time independent Schrodinger equation for my system, I'll end up with this, and in matrix form I can also express it in this form. If you see this expression carefully, it provides us a linear relation between what will happen to the wave function over neighboring sites. So if I have information over this, then by applying this transformation, I can have information over the next neighboring sites. This will be helpful in calculation of localization length. We'll see that later on. So jumping on to numerical results in one-dimensional system. So we have these 4 different diagrams. So they show you is, so let's consider a free system like zero disorder system, which I talked about earlier. So I said its results, the wave function, is just this free particle wave function. So calculating the probability, which is chi square, mod chi square. So we have this free particle behavior here, which is nothing, just Bloch waves in case of lattice systems. But this case is only for the zero disorder system. So as I keep on increasing disorder, we see in case of disorder strength 2, 4, and 10, we have these particular results. So this blue and orange lines, they basically show the probability for a wave function with a particular energy that I took as my input parameter, and it shows this localization behavior around this particular sites, and it's less probable to be there on these sites. I performed this results again, and in this case I found out to be like the probability here was less as compared to probability finding here. So this blue and orange is nothing but performing the same simulation twice, and we've clubbed these results within the same graph. So as we see that if we increase the disorder in this system, in case of one-dimensional systems, we start seeing this localization behavior. It's not uniformly distributed as in this case. So if I keep on increasing the disorder, it keeps on localizing itself to very narrow band of lattice sites. So if I again increase the disorder, we see it's like a point behavior here. So with the increasing amount of disorder, it kind of localizes itself to a very less number of lattice sites. This followed by increase in disorder, where it's just kind of a delta function. So I'll try to provide you a different perspective into the same thing. So here in figure A, what I have plotted is energy versus the localization length behavior for different disorder strengths. So the localization length is calculated as this. It gives you an idea about how much number of lattice sites is a particular electron distributed over. So if you see here, like for a particular energy level, say 0.5, so what it will show you is the localization length for the wave function which was having energy close to 0.5, and its localization length was how much. So basically for 0.5 energy, we see that for very low disorder, like disorder strength is 1 here, we have large number of we have very large localization length, so that the electron is distributed over a large number of lattice sites, which decreases as we keep on increasing the disorder in the system. So it decreases, 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 and further reduces to 0, because as I showed you, for a very large disorder value, this was just a kind of a delta function. So the localization length, for no matter which energy of the wave function we choose, it always reduces to 0, because it's localized over one particular site. Moving on to figure B, as I told you in the second slide, so localization can also be studied by the time propagation of a wave packet. So what I did was, I placed a Gaussian wave function, so not a Gaussian, really a delta function at position 0. So basically, I placed an electron at a lattice site 0, and then allowed it to time propagate following this time dependent Schrodinger equation. And I have plotted the results here for different disorder strengths at time t is equal to 100. So basically, here we can see that when the disorder strength was very less, so the electron which was initially localized over this 0 site, it then kind of dispersed over whole number of lattice sites from -80 to 80, depends upon how I choose my origin. So it kind of got delocalized over almost all the available lattice sites. Whereas when I increased the disorder strength, it kind of localized itself to sites very close to position 0, and on further increasing the disorder strength, it just kind of limited itself to even smaller number of lattice sites. So if I increase the disorder strength further, say 10 or 20, so it will just stay here no matter how much you time propagate the wave function. So the combined purpose of all these diagrams was to show you that with a slight increase in the disorder strength, we have a drastic amount of localization which we can visualize in the system. So here with a very small disorder, we can see this and this, and then further increasing and increasing. Here also the localization length decreases, which also shows the same trend. Time propagation of the initially localized wave packet also shows you this, that no matter how long the time you take, if your disorder strength is very, very large, it's gonna stay there forever and ever. So moving on to 2D systems, here also I have taken just a square lattice, 50 cross 50 lattice, and for disorder strength 0, this is what this green dots and the yellow dots are basically the density plots in the 2D lattice system. So here you see it's delocalized over the whole lattice sites, whereas as I increase the disorder strength, it kind of localizes itself to particular regions. The yellow ones are the high density regions that I have. Similarly, the time propagation thing that I showed you here in the one-dimensional systems, what I did was I placed the electron here at 0 disorder strength. So, and then I allowed to time evolve its state for about 50 seconds, and this is what I got as the result. So basically, initially it was localized here with a slight with an exponential decrease over this length systems, and then for disorder strength 2, it kind of delocalized to this whole system, and then for a very high disorder strength, you see that it kind of localizes itself to the same state where it started from. On to numerical results in case of three-dimensional systems. So as we talked earlier, there is something special about 3D. So here we have something called the critical strength, which was also suggested to us by the scaling theory. So here are the results. So if I have, so the figures A, B, and C, they kind of show you the density projections of the wave function for a given energy, which I have taken as my input parameter. When the localization or when the disorder strength in the system was less than the critical disorder. Basically, it means that epsilon was less than the epsilon critical. So This A, B, and C figures, they show you X, Y, Y, Z, and ZX plane density projections of that particular wave function with the energy that I choose. So here you can see it's delocalized over the whole system with a few particular high density regions and then followed by some low density regions. But in case of disorder strength, which is greater than the critical strength, we can clearly see that the system was localized to where it started from only. And this is the XY plane projection, YZ, and then ZX plane projection for this end system. And we can see that it's delocalized over just this much number of lattice sites. And if I increase the disorder strength further, it will just gonna delocalize to just 1 or 2 lattice sites. Another important thing to note here is that in the figures A, B, and C, the disorder strength is taken to be 6. As you can see in case of 2D and 1D systems, where even a slight disorder of around 2, 3, and 4 was clearly showing the localization behavior. Here in case of disorder strength 6 even, we are not seeing any kind of localization in these 3 diagrams. This is because, as I mentioned earlier, as long as the disorder is less than the critical value, the disorder strength is less than the critical value, we may not see, in fact, any kind of localization behavior in the system. I hope these numerical results were enough to provide you an insight into what actually is meant by Anderson localization for 1D, 2D, and 3D systems. So now I would like to brief you about how actually we study the disordered systems. Normally what is taught in higher classes is the ideal tight binding model with no fermionic interactions and no disorder in the system. It's just a perfect lattice system with no correlations. So an important thing to study the disordered systems is the probability distribution function or the probability density function. So probability density, because most of the times it's not that we have whole information about the system. Our information is just limited to various moments or the cumulants. These moments and cumulants are something that provide us an insight into what's actually happening in the system. So sometimes what we, in case of non-self-averaging systems, what we have is the PDF function is literally too broad that we need infinitely many moments to characterize the properties of the system. So in case of Anderson localization, when the system is very close to this metal to insulator transition, so what happens is the electronic quantities, they vary too quickly, and this probability density and its probability density function was calculated, and it came out to be a log normal distribution. So log normal distribution is kind of a left skewed normal distribution, you can say. It's not exactly a left skewed distribution, but like it will give you an insight of how it actually looks like. And the perfect example for this kind of probability density function was found out to be the local density of states. And recently I was going through some papers, and it also showed that for various lattice systems in 2D and 3D, the system size dependence on this local density of states was actually a good indicator for this Anderson localization in the system, and it actually agreed over tens of orders of magnitude, which is actually quite good result. So and generally when we talk about means and cumulants, the first thing that strikes our mind is the mean of the distribution. But in case of log normal distribution, it's not actually the mean that provides us the centrality parameter. It's not appropriate for the log normal distributions. In case of log normal distributions, what we have is the geometric mean of the local density of states, which will provide us the information about the system. An important point about the geometric mean is that it vanishes when the critical disorder strength is reached. So if you have a disorder strength in the system which is greater than the critical disorder strength, then it kind of vanishes. But an important point to note here is that it is not an order parameter of the system. Moving on to models for disordered lattice systems with the correlated fermions. So the Hamiltonian that I showed you previously for the tight binding case was just limited up to this and this. And in general, this is how we write Hamiltonian for an interacting system with the disorder strengths. So basically here the Ci dagger and Cj sigma are basically the fermionic creation and annihilation operators. This n here is the number operator, and this Tij, as mentioned earlier, it represents the hopping amplitude. So now we have different models for the system. In case of Hubbard model, this Tij sigma is assumed to be independent of the spin part. So basically, no matter if it's no matter what the spin of the particle is, its hopping amplitude is independent of this. So no matter what the spin of the particle is, it's equally probable to move towards its left side and its right side, regardless of its spin. Whereas in case of Fedorkov model, it's just only the spin up states that are allowed to hop from one lattice side to the other lattice side, while the spin down states, they are localized to the particular lattice site. So only the spin up systems, they are able to hop, and the spin down systems are localized to a particular lattice site. There are a lot of other models also available for the study of different systems. So here in the second term, this is how the Hamiltonian breaks the lattice symmetry by adding an extra random potential. And the third term is basically the two body interaction term. So it increases the energy of a particular lattice site when it increases the energy if the two fermions of opposite spin occupy the same site. So as we can see here, the disorder affects the system through these particular epsilon i's, which I took out to be uniformly distributed between minus epsilon by 2 to epsilon by 2. So here what we do is, in general, epsilon i's are drawn from a probability density function, and then for n number of lattice sites, and it generally is just the product of these different individual probability functions, probability densities, and each of this p epsilon I is actually the same and the normalized probability density function for atomic energies. So we have now, we can kind of classify disorders into two particular categories, that is the quenched disorder and the annealed disorder. So basically, in case of quenched disorder, what we assume is that these individual atomic energy related probability density functions are time independent. So what it means, in other words, is that the distribution is random, but it does not change with time. So, but in case we want to have a more realistic image of how disorder behaves, we have to consider the annealed disorder, where these random and atomic energies are allowed to fluctuate in time. So talking about the solvability of this Hamiltonian mentioned here, what we have is, in the case of zero disorder limit means these epsilon i's are basically neglected, zero, and it's solvable only when there is no interaction in the system. So the solution in this case is just obtained by simply taking the Fourier transform of this Hamiltonian, and in case of finite disorders, the solution exists only when there is no hopping allowed in the system. So its partition function is given by this function, and since we are not allowing hopping for the electrons, the spectrum is just the point-like, and the thermodynamic in limit, it's just showing you the localized. It will just show you the localized eigenstates. In the general case, where u is equal to 0 still, but you allow hopping and disorder both to act upon your system, the Hamiltonian is not exactly solvable. But in the paper by Anderson and Thouless and above, this was solved by taking the hopping to be independent of the spin part between the nearest neighboring sites only. So the solution was expressed in the form of one particle Green's function, which allows you to kind of relate to the propagators and study the time evolution of the system. Instead of solving this time dependent Schrodinger equation, you can also take another pathway through this Green's function and by calculating the propagators. So the further analysis of this Hamiltonian is done using dynamical mean field theory, which is beyond the scope of my term paper. Uh, Thanks for bearing with me for this long. I hope I was able to justify the amount of time that I took, and this presentation was helpful enough to provide you an insight into what is meant by Anderson localization and how actually we study the disordered systems. Thanks.